Hello friends, welcome to the lecture of integral equation with Fredholm integral equation with the symmetric kernel. So if you remember, we have discussed certain theorems corresponding to Fredholm integral equation with symmetric kernel. So first theorem we have discussed is that if a kernel is symmetric, then all its iterated kernel are also symmetric. And second result, which is kind of hunting license to start with, that is every symmetric kernel with a non-zero norm has at least one eigenvalue. So this is the beginning point by which we want to start our theory. So third is that if we have more than one eigenfunction corresponding to distinct eigenvalues, then they are orthogonal to each other. And theorem 4 says that the eigenvalues of a Fredholm integral equation with a real symmetric kernel are real. Okay, and next result is, which we have discussed, is that the multiplicity of any non-zero eigenvalue is finite. So multiplicity is the number of linearly independent eigenfunctions corresponding to a given eigenvalue is always finite, provided we have a symmetric kernel and this quantity is finite. So this we have discussed in a previous lecture. Now let us utilize the proof of this theorem 5 to prove one more result, which says that the eigenvalues of a symmetric L2 kernel form a finite or an infinite sequence with no finite limit point. It means that when we have a sequence of eigenfunctions, if it is finite, then no problem, but if it is infinite, then we don't have finite limit point, so they will converge to infinity. So for that we just look at that. Suppose we have a sequence, say lambda i's. So we have a sequence, say lambda I, and the corresponding eigenfunction we are denoting as phi of x. So without loss of generality, we can assume that all these phi I x are all orthonormalized by Gram-Schmidt process. Now if you remember, in previous proof we have simply approximated your k of xt as summation your ai phi I x here. So I is equal to whatever I is we have. Okay, so here we are taking the summation of over ai. So this is the beginning point here we are assuming. So here I am assuming that ui bar lambda I lambda t is your eigenfunction corresponding to lambda. So if you drop this notation lambda, then you can say that it is nothing but this. So here we are assuming that kxt is approximated by ai ui bar t. So here ui bar t is the correspond eigenfunctions corresponding to your eigenvalues lambda I. Is it okay? So in a same way you can define your ai. ai is basically a to b kxt ui t dt. So I am dropping this lambda because we are considering all the eigenvalues. So if you remember that ui is the eigenfunctions corresponding to, say, lambda I eigenvalue. So here I am assuming that if we have repeated say eigenvalues, we count them as lambda 1, lambda 2 and so on. So it may happen that lambda 1, lambda 2 may be equal and same as lambda, but we are counting all the eigenvalues. Okay, so we are saying that this ui is the eigenfunction corresponding to lambda I. So here ai is nothing but lambda I inverse ui x. So here I am writing here, let me use this notation since I am using this. Let us assume this phi I is replaced by your ui. So this is ui, x is the eigenfunction corresponding to this lambda I. So I can write it like this. So here we have, say, ui bar, because if this is eigenfunctions, then these are also eigenfunctions. Okay, so here I can approximate kxt by this. So here ai is basically what? ai is a to b your k of xt and ui t dt. Now this is since by the property of eigenfunctions, this is 1 upon lambda I your ui x Is it okay? So here ai you can get it like this, 1 upon lambda I ui x. Then again we can use Bessel's inequality, and you can have this property, this equation 11. So along your equation number 11 you have this a to b k of x t square dt is greater than or equal to summation 1 upon lambda I square, and it is what, modulus of ui t square. This is x, I think. So this is x here. Okay. Yes. Okay. So now again now let us again integrate with respect to x. So a to b dx here. Then here we have a to b d of x, right? And we are simply assuming okay, so this I can consider, since this ui x are all normalized, then I can write this as that this is greater than or equal to summation 1 upon lambda I squares. Is that okay? So let me use the, okay, so here we have this thing. Is it okay? Now if this quantity is finite, okay, so here if this quantity is finite, then we can say that, okay, let me write it here, then this series summation 1 upon lambda I square is, sum is going to be finite. Now sum is going to finite means your infinite series of 1 by lambda I square is convergence series. And if you remember, there is a small result that if a series converges, then its nth term is tending to 0 as n tending to 0. So it means that this implies that limit n tending to infinity, your 1 upon lambda n square is basically tending to 0. Or equivalently we can say that this implies that limit n tending to infinity, your lambda n is going to be infinity. So there are only two possibilities, that this sum is finite. If this sum is finite, no problem, and if this sum is not finite, then we can use this property of convergence series which says that your nth term is tending to 0. It means that your lambda n is tending to infinity. So it means that either your, so this proves this thing, that the eigenvalues of a symmetric L2 kernel form a finite, if it is a finite set, fine, or if it is an infinite sequence with no finite limit point. Now this is a rough sketch of the proof. The exact proof or a very rigorous proof of this book is this proof is given in the book by R.P. Kamal, linear integral equation. So now let us move a little bit further, which says that theorem 7, it says what, let the sequence phi n x be all the eigenfunction of a symmetric L2 kernel kxt with lambda n as a corresponding eigenvalues. So here we have we are able to calculate all the eigenvalues and eigenfunctions. Then with the help of this we try to define a new quantity which is known as truncated kernel, which is what, if it is first kernel, so it is k1xt is your kxt, and your k2xt is basically kxt minus this quantity phi 1 x phi m bar t lambda m. So it is kind of, we are approximating your kernel kxt by the this thing. So here basically we are doing like this. Is that okay? So here we try to find out, say as accurate as 1. So here we are truncating I equal to 1, first approximation 2, 3 and so on. So here we are defining that at nth plus n plus 1th place it is given by this. So kxt minus m equal to 1 to n phi mx into some constant. That constant I am writing as phi m bar t upon lambda m. So it is kind of approximation of kxt at with the help of m, first m eigen functions. So we call it n plus 1th truncation of this kxt. So this is known as truncated kernel. Now we can prove that this truncated kernel has the eigenvalues lambda n plus 1, lambda n plus 2 and so on, which is corresponding to phi n plus 1 x, phi n plus 2 x eigenfunctions. So and this kernel will not have any other eigenvalues or any other eigenfunctions. So this is corresponding, so it means that if we already know that eigenvalues and eigenfunction, then we can always find out eigenvalues and eigenfunction corresponding to this truncated kernel. Now what is the use of this? We are trying to with the help of this, we are trying to approximate your symmetric kernel with the help of these kind of separable kernel kind of thing. So here if you remember, there is a result in a separable kernel, that if we have a separable kernel, then eigenvalues are finite eigenvalues. Now here if I look at that theorem 8, which says that a necessary and sufficient condition for a symmetric L2 kernel to be separable is that it have a finite number of eigenvalues. So it means that this is a if and only if result, that if we have finite number of eigenvalues, then it means that at some point this process will stop. So it means that suppose we have, say we have only n eigenvalues, then we can have say only n eigenfunctions. So it means that at k n plus 1th stage, this is nothing but we cannot get k n plus 1 xt, so it is simply 0. So in that case your kxt is written as m equal to 1 to n phi mx phi m bar t lambda m, or we can say that this is nothing but given in terms of separable form. So if we have only finitely many eigenvalues, we can say that in that case your kxt is given by this separable form. Or if I say that we don't have if it is separable, then we already know that we have only finite number of eigenvalues. So if it is finite number of eigenvalues, then it is separable. If it is separable, then we have only finitely many eigenvalues, that we have already done. So here with the help of theorem 7, we can say that if we have finite number of eigenvalues, then kxt can be written as this kind of form, which is nothing but a separable form for this kxt. So it means that a symmetric L2 kernel is separable if and only if we have finite number of eigenvalues. Okay. So now let us move to the next result, which is a very important result of Hilbert Schmidt, known as Hilbert Schmidt theorem. It says that, again we are taking this without proof, but statement is very important. Let us say that if we have a function f of x which is given by kxt gt dt, or we can say that which is generated by a kernel k and a function g. Here we are assuming that this kernel k is a symmetric L2 kernel, and g also we are assuming that it is L2 function. Then Hilbert Schmidt theorem says that then this function f of x, which is generated by this k and g, can be expanded in an absolutely and uniformly convergent Fourier series with respect to orthonormal system of eigenfunctions psi 1 psi 2 of the kernel k. So it means that what it says, let me explain in a little bit detailed manner. It means that if we have f of x is equal to your k of xt gt dt. So here we are assuming that kxt belongs to L2, and similarly your gt k and g both belongs to L2. Then your Hilbert Schmidt theorem says that fx can be written as summation of some am phi m x, and summation over this m is say 1 to infinity. Now what is this phi m? So here phi m is the eigenfunction corresponding to this kernel kxt. Means what? That it satisfies this property that that phi mx is equal to lambda a to b, and kxt phi m t dt. So it means that this phi mx is basically eigenfunction corresponding to some eigenvalues for, let us say, that lambda m, and it satisfies this property. And in addition, we are just assuming that this can be orthonormalized to say psi 1 2 and so on, psi 1 psi 2 and so on. So here we can write this as f of x equal to summation m equal to 1 to infinity am psi mx. Now what is the difference between this and this? The difference between this and this is that here it is eigenfunction. Now by a Gram-Schmidt orthogonalization process we can convert into new systems with having equal number of elements here, but now with the property that they are orthonormalized. Is it okay? So it means that fx can be written as am psi mf psi mx, and here am you can write it as fx a to b and psi mx d of x, and just for simplicity we are writing this as f of, we are denoting this as f of m. So if you look at equation number 13, it says that if we have this function fx which is given by this, then this fx can be represented as this infinite series which is absolutely and uniformly convergence. So here f of m is given by this f psi m, which is denoted by this a to b f of x psi mx d of x. So this is the inner product we are defining as a to b f of x psi mx d of x. Is that okay? So these coefficients are known as Fourier coefficient here, and then this Fourier coefficient fm is related to Fourier coefficient corresponding to g. So here I can say that this fm is given by g of m divided by lambda m, where gm is the Fourier coefficient of g, and lambda m are the eigenvalues corresponding to say psi m, and it is eigenvalues of the kernel k. This is not very difficult here. So what we can do here is to find out this relation 14 fm equal to gm divided by lambda. What we can do here, we have this, then we simply multiply by say phi mx, and then use a property of orthogonality. Let me write it here. We have this, okay. So here let us say we have this, we have say f of x phi m x here. So here let me write it f phi m, right. So this I can write it f phi, f is what, let me denote this as kg. So this is denoted as, defined as k operating on g. So this is kind of an operator on this. So k of g, kg is defined as this, okay, limit is say a to b. So kg phi of m. So this you can prove that this is same as g k star and phi m. Now since k star is same as k, because we are assuming that it is a symmetric kernel, then it is nothing but g k of phi m. Now we already know that k of phi m means this kxt phi m t dt. So this is going to be phi m x divided by lambda m. So this is what, this is nothing but g your phi m divided by lambda m. Is that okay? So this is you can write it, you can take out 1 upon lambda m out, this is g phi m, and this is nothing but gm, we are defining it like gm. So gm by lambda m. So here fm, this is nothing but your f of m. So fm, which is a Fourier coefficient of f with respect to phi m, so fm is given by gm divided by lambda m. So here you can look at that equation number 14 is valid in this way, that fm is given by gm divided by lambda m. Is that okay? So using this, now let us proceed to solve your Fredholm integral equation of first we try to solve for second type, and then we, if we have we will discuss for first integral also. So let us try to solve solution of a symmetric integral equation of non-homogeneous Fredholm integral equation. So please remember, if it is homogeneous, then we already have solved, that is nothing but your eigenvalue eigenfunction problem. Okay, so now let us proceed for solving a non-homogeneous problem, that is y of x equal to f of x plus lambda a to b kxt yt dt. Here I am assuming that k is L2 kernel, so that we can utilize the theory which we have discussed earlier. Okay, now we assume that this lambda is not an eigenvalue. We will consider the case when lambda is an eigenvalue, but for the starting point let us assume that lambda is not an eigenvalue, and we are able to solve the homogeneous problem, means we are able to find out all the eigenvalues corresponding to this symmetric kernel K. So here we are assuming that lambda 1 lambda 2 are the eigenvalues of the kernel kxt, and this psi 1 psi 2 are orthonormal system of eigenfunction of the kernel kxt. So that we already have inquired. So theory says that you can always do it. Okay. So now using the Hilbert Schmidt theorem, this yx minus fx is written as lambda kxt yt dt. So now you can use Hilbert Schmidt theorem and say that this yx minus fx can be expressed as this infinite series in terms of eigenfunctions corresponding to this kxt, which is uniformly and absolutely convergent here. So so this is by your Hilbert Schmidt result, and here we try to find out now this Fourier coefficient, that is am. So that we know that am is basically what? Am is nothing but yx minus fx psi star mx dx. So here your inner product is defined like this. Let me use it. So we already know this, that yx is equal to f of x plus lambda a to b kxt yt dt. Now you can take this out, so yx minus f of x this side, and it is lambda a to b k of xt yt dt, and then using Hilbert Schmidt theorem you can always write it like this as am, and here we are assuming that psi mx dx, and how to find out this am? Am is nothing but Fourier coefficient corresponding to this yx minus f of x. So that is yx minus f of x, and then you sim star x dx a to b. So you calculate. So if you calculate this, this is what? This you can write it, you just take it, you separate these two integrals. So yx psi star mx dx minus fx psi star mx dx. So where psi m star is a complex conjugate of psi mx. But if you look at your previous thing, that your Fourier coefficient corresponding to your function f of x can be written as Fourier coefficient of the unknown function given function gx as this fm equal to gm by lambda m. So here in an analogous manner you can say that am, which is a Fourier coefficient of yx minus fx, can be written as Fourier coefficient corresponding to this yt. So I can write it here am as lambda ym divided by lambda. So you can equate these two things. So when you equate these two things, you can get your am and ym. So am is the Fourier coefficient here, and it is written as lambda fm divided by lambda m minus lambda. This is very easy. I can say that here we have am as ym minus fm, and this is coming out to be lambda ym upon lambda m. So if you compare, you will get ym as 1 minus lambda upon lambda m is equal to f of m. So you can get, once your ym is calculated, then you can calculate your am also. So here you can get am as lambda fm upon lambda m minus lambda, ym equal to this. Okay, fine. So this is something which we want to find out, ym. Okay. So now I can write it yx as what? So y, since look at here equation number 16. So yx minus fx is equal to m equal to this summation m equal to 1 to infinity am. Am is you have already obtained and psi m is already known to you. So you can get yx in terms of fx plus this infinite series. So you can write it here yx equal to fx plus lambda. I am writing the value of am. So am value of am is lambda fm upon lambda m minus lambda. So I can write it here lambda fm upon lambda m minus lambda psi mx dx. Now here you can utilize the value of fm. Fm is what? Fm is the Fourier coefficient of f, which is nothing but this a to b. I am not writing the limit because your interval may be anything. So here fm is basically what? Ft psi star mt dt. So using the expression for f of m, and I am using t as the integrable variable because we are already having x. So here fmt I am writing as a to b psi m star t ft dt. So when you write it here, and we already know that this series is absolutely and uniformly convergent, so we can always interchange the integral sign and summation sign. So we can write it like this: f of x plus lambda m equal to 1 to infinity this thing. Now if we denote this m equal to 1 to infinity fm upon lambda m minus lambda, or you can say that if we denote this gamma xt lambda as this m equal to 1 to m psi m is x psi m star t lambda m minus lambda, and say that it is resolvent kernel, then your solution, it can be written as this. So here your solution is given as y of x is equal to f of x plus your lambda times a to b gamma x t lambda, your f of t dt, where gamma x t lambda is given as this infinite series m equal to 1 to infinity psi this is psi m x psi m star t divided by lambda m minus lambda. Okay, and this series is absolutely and uniformly convergent. Okay, so here solution is given by this. Now if you look at here, your lambda, choice of lambda is very important, because if lambda is one of the eigenvalue, then this gamma xt lambda will not exist. So here I am assuming that the singular point of this resolvent kernel is the values of lambda which is equal to lambda m, or you can say that the singular point of the resolvent kernel gamma corresponding to a symmetric L2 kernel are simple poles, because it is simple pole and every pole is an eigenvalues of the kernel. Or you can say that for lambda equal to eigenvalues is your the singular point of this kernel gamma resolvent kernel gamma xt lambda. So using this, now let us try to apply the result for actually solving the Fredholm integral equation of the second kind. Okay, so that we are going to do it in next lecture. Thank you very much.